Question 1, part C. This time I'm going to find the minimum spanning tree using Prim's algorithm. The question doesn't specify whether we have to use Prim on the matrix, which we completed in part B, or whether we can do Prim on a network. And in this video, I'm going to carry out Prim's algorithm on the network. There's a reminder in the question that we must clearly state the order in which we consider the vertices and the order in which we include the arcs. So down the side here, I'm going to make a list of the edges in the order that we add them to the tree. And unlike Kruskal's algorithm, Prim doesn't involve any rejections. If you remember Kruskal's algorithm, we start by listing the vertices in ascending order of size, and then we go through accepting or rejecting them. Prim's algorithm is different. We are told, well, we're usually told where to start. If we're not told where to start, then that's our choice. We can start wherever we like. For this question, I'm told to start at A. Now, starting at A, the first edge I add to my minimum spanning tree is the shortest edge, which connects with my current tree, and at the moment my tree is just a single vertex, which is A. So to begin with, my two choices are AC, which is 30, or AB, which is 31. Obviously, the smallest of those is AC, 31. So that's the first edge in our minimum spanning tree. So I'm going to list here AC, which has a length of 30. That's the first edge in our tree. So I don't need to say which edges I've rejected. That's not involved in Prim. Prim is just to end up with a list of the edges that we added to the tree. Each time I will mention all the options. I don't write down any rejections. Right, so our edge is now our tree is now a single edge with two vertices. The next thing I need to look for is an edge which connects a new vertex to the current tree. So let's look. I can either choose AB or DC or EC or FC. So those four numbers are my only options. I couldn't choose DE because that doesn't connect with my current tree. This is how Prim's algorithm works. Each time we look for an edge that brings a new vertex into the tree, and it must never not be connected. So again, that's why I couldn't choose, for example, DE, because then my tree is not connected. And with Prim's algorithm, the tree is always connected as we go through the algorithm. So once again, my options are AB, which is 31, or CD, 22, CE, 24, or CF, which is 29. The smallest of those numbers is clearly 22, so CD, 22, is the next edge. So CD, 22. Once again, I'm going to run through all the options I have, and the options will be all edges which connect a new vertex to my current tree. And my current tree has two edges, three vertices. So I could choose AB 31, or I could choose DB 24, or DH 34, or DE, which is 18, or CE, which is 24, or CF, which is 29. I couldn't choose, for example, FG, which is 21, because that doesn't connect with my current tree. So out of all the options, 18 is the smallest. So my next edge in the tree is DE, which is 18. My tree now includes A, C, D, and E. I'm just going to take a moment to mention that when we carry out Prim's algorithm, there is never any danger of a circuit or cycle. It's because we're always looking to connect a new vertex to the tree. So at this stage, it is not an option to choose CE next, because that uses C and E, which are both already part of my tree. So that CE is not an option. The options now are AB, 31, or DB, 24, or DH, 34. Remember, CE is not an option. It doesn't connect a new vertex. EG is an option because it connects G. Likewise, EF would be an option, and CF would be an option. Out of all those options, 24 for BD is the smallest number. So BD 24 is the next edge. Moving on, the options. Well, now AB is not an option because A and B are already in the tree. So AB not an option anymore. Likewise, CE not an option either. So I need to choose from BH, DH, EG, EF, and CF. Out of all those options, 26 for EG is the smallest. So EG 26 is the next one. EG 26. Now, just like Kruskall's algorithm, Prim's algorithm stops when every vertex is included in the tree. At the moment, H and F are the only vertices not included in the tree. So we'll stop after adding 2 more edges, because I know with Prim's algorithm, every edge brings a new vertex into the tree. So now I need 2 more edges. Options now. Remember, AB not an option, CE not an option. My options are CF, EF, or GF. They would connect F. Or BH, DH, GH. Out of those options, the smallest is 21 for FG. So that's my next edge, which leaves only one vertex, H, not part of the tree. So one final time, I'll just point out which edges are now not options. AB not an option, doesn't connect a new vertex. CE not an option. CF no longer an option, it doesn't connect a new vertex. Same for EF. My only options are DH, because that connects H to the current tree, or DH, or GH. Out of those 3 options, clearly 33 is the smallest, so GH 33 is the final edge added to the tree. For part C, 3 marks, I've now got all 3 marks. And one more time, remember with Prim's algorithm, there's no such thing as rejecting an edge. We just end up with a list of edges in the order that we added them to the tree. While we're here, I'm just going to do part D. Part D just says write down the total weight of the tree. So adding these numbers up, we get 174. There is a quick check we can do, because part A of this question, we had to use Kruskall's algorithm to find a minimum spanning tree on the same network. Now they might give us slightly different trees in that they use different edges. However, they will both definitely have the same total weight. So they are both minimum spanning trees. So if I add these numbers up, I get 174. I would then check my answer to part A and add my edges up from part A. If that was also 174, that's a good sign that I've done both A and C correctly. If they weren't the same number, I need to go back and try and find what I did wrong in either A or C. That's the end of question 1, part C and D.